9.4 Lesson 2, Comparisons of Series. Our objective for today is only one objective. Our objective for today is you'll be able to use the limit comparison test to determine whether a series converges or diverges. Vocabulary for today is the limit comparison test. So you need to remember some algebraic skills to be successful with the calculus in this section. So we had these two problems for you to do. Simplify the quotient. So what you see here is a complex fraction. We call this a complex fraction because you have the division bar, and in the numerator you have a fraction, and in the denominator you have a fraction. And of course, you know how you should simplify that. How do you do division? You multiply by the reciprocal of the divisor. So that's the basic algebra that you need. And when you do that, this is what you have. The square root of n squared minus 4 over 3n. And again, you have the same thing with number 2. You have a complex fraction. So how do you simplify the complex fraction? You're going to divide the numerator by the denominator. So you have to multiply by the reciprocal of the denominator. And when you do that, you get 3n over the square root of n squared minus 4. So you'll see a relationship between the first and the second problems. In the first problem, the dividend is 1 over n, and the divisor is 3 over the square root of n squared minus 4. And in the second problem, they're switched, so that the divisor from the first problem is the dividend in the second problem, and the dividend from the first problem is the divisor in the second problem. Now, this is something that you will see with the limit comparison test. So let's look at what we mean by the limit comparison test. Yesterday we looked at the direct comparison test. You can apply the direct comparison test when you have series with positive terms, and you need to have a comparison series. And the second step is you needed to have been able to compare the nth terms of the two series. Sometimes you may not be able to establish the term-by-term comparison that would allow you to use the direct comparison test. Maybe you have a divergent series, and when you try to do the term-by-term comparison, what I mean to say is maybe you have a comparison test. What I mean to say is maybe you have a comparison series that is divergent, and you're trying to apply the direct comparison test. The only way you'd be able to apply the direct comparison test to prove divergence is if you can show that the terms of the series that you're considering is larger than or equal to the terms of the divergent series. If you can't establish that, then you can't use the direct comparison test to prove divergence in the example that we're talking about. So sometimes you may not be able to use the direct comparison test because you wouldn't be able to establish that direct comparison between nth terms of the two series that would allow you to appropriately use the direct comparison test. In those cases, we have another test called the limit comparison test. So here's the limit comparison test. Suppose that you have two series and both of them have positive terms. And then you're going to take the quotient of the nth terms of the two series. And you're going to take the limit of that quotient as n approaches infinity. And if that limit is finite and positive, then either both series converge or both series diverge. Yesterday we actually looked at the proof of the direct comparison test. The proof of the limit comparison test is in your textbook, and I will only say right now that the proof of the limit comparison test relies on the direct comparison test. So the proof of this limit comparison test uses the direct comparison test to argue that this has to be true. And you can see that in your textbook. As with applying the direct comparison test, there are certain steps when you would like to use the limit comparison test to argue that a particular series must converge or diverge. And the steps are similar to what we did yesterday with the direct comparison test. Step one is you must choose a comparison series. The first step, just like yesterday, is to choose a comparison series. There are two criteria that you should use to choose a comparison series. The first one is your comparison series should be such that it is easy for you to determine the convergence or divergence of the comparison series. And the second criteria is because the limit comparison test is asking you to find the limit of the quotient of the nth terms of the two series as n approaches infinity, you should choose a comparison series such that that limit will be easy to evaluate. So there are some guidelines to help you with that. So if you look over here, we have some guidelines. So again, you can read the short paragraph above the examples. The limit comparison test works well for comparing a messy algebraic series with a p-series. A p-series, they make good comparison series because it's easy to know if a p-series converges or diverges just by looking at the value of p. In choosing an appropriate p-series, you must choose one with an nth term of the same magnitude as the nth term of the given series. That particular part that I just read has to do with criteria 2. You want to choose a series so that it would be easy for you to evaluate this limit. So let's look at some examples here. So if you look at this particular given series and you want to know whether that series converges or diverges, you see that you have in the denominator 3n squared minus 4n plus 5. So a good comparison series would be a p-series whose p-value is going to be 2. Why 2? Because in the denominator of the given series, we have n raised to the second power. And the reason why this makes a good comparison series is because, one, we know that this p-series will converge because p is equal to 2. And number 2, if you choose that, it would be easy for you to compute the limit from the limit comparison test. And we'll see a couple of examples later. But I just wanted to go over some criteria for choosing a comparison series. After you choose a comparison series using these two criteria, you will then proceed with the limit comparison test by applying step 2, which is to find the limit from the limit comparison test. And if that limit exists and is a finite positive number, that's what it means for the limit to exist. The quotient has to approach a number as n approaches infinity. So if that limit is positive, then you can conclude by the limit comparison test that your series either converges or diverges depending on whether your comparison series converges or diverges. Because if you look at the limit comparison test, it says when you do the comparison and you get this limit to be a positive number, then the two series either both converge or both diverge. So how do you know if your series that you're considering converges or not? You look at the convergence or divergence of the comparison series and apply the limit comparison test. So we'll look at our first example here, number 16. The instructions are: use the limit comparison test to determine the convergence or divergence of the series. So our first step is to choose a comparison series, and we have two criteria when choosing the comparison series. The first one is it should be easy for us to determine the convergence or divergence of the comparison series. And the second one is we should choose a comparison series so that this limit from the limit comparison test will be easy to compute or easy to evaluate. So you have to look at the nth term of the series that you're considering. And we're considering the series that's given for number 16. If you look at the nth term, One thing that you'll notice is that you've got a constant 2 in the numerator, and then you're subtracting a constant 5 from the denominator. But the term that actually has n in it is this one here, and that's 3 to the n. So you might think, if it would be nice if my comparison series also had 3 to the n in it, because if it does, when you form the quotient that you need to form for the limit comparison test, having 3 to the n as a part of the nth term in the comparison series might allow for us to take the limit that we have to take more easily. And it turns out that a geometric series with a common ratio of 1/3 would do the job. So here's our comparison series. So here is our comparison series. It is a geometric series, and geometric series are really easy to work with to determine convergence or divergence. You just need to look at the absolute value of the common ratio. And the other criteria because of which we're choosing this to be our comparison series is looking ahead at the limit that we have to take. And it helps that we have 3 to the n as a part of the nth term for the comparison series. But this is a geometric series with absolute value of the common ratio equal to 1/3, which is between 0 and 1, so our comparison series converges. The next step is the following. You have to take the limit of the quotient of the nth terms of the two series as n approaches infinity. And if that limit is finite and positive, then we may conclude by the limit comparison test that our series for number 16 must converge, because the comparison series converges, so the series that we're considering must also converge. So when you form that quotient for the limit comparison test, you can form the quotient either way. You can either put the nth term of the comparison series in the numerator, or you can put the nth term of the comparison series in the denominator. It doesn't matter which way you do it, except that you want to do it for some problems. One way will be easier to find the limit than the other. So you want to keep that in mind. But that's the only consideration that you have to have for choosing which term goes in the numerator and which term goes in the denominator. So let's try it one way. So step 2 is to find that limit. So I chose to form my quotient this way, and that's fine. And now you can go ahead and simplify the complex fraction here using algebra that we began our lesson with. So multiply by the reciprocal of the divisor, which is 3n over 1. So you have 2 times 3n in the numerator. So the next thing that you can do is you can factor out the constant 2, and when you do that you'll have this. And now we just have to evaluate the limit. And how can we evaluate the limit? You can use L'Hopital's rule, because as n goes to infinity, both the numerator and the denominator will go to infinity, giving you the indeterminate form infinity over infinity. So we can use L'Hopital's rule. And if you want to be technical, you can change n to x and use L'Hopital's rule on the real valued function. But of course, the limit of what we're looking at will have the same value as the limit of the corresponding real valued function as x goes to infinity. So when you take the derivative of the function in the numerator, you will have natural log of the base times 3 to the n. And when you take the derivative of the function in the denominator, for the first term you'll have natural log of the base times 3 to the n, and the derivative of 5 with respect to n is 0. So now what you have here is a form of 1. We can cancel the common factors, and what you see is that you have 1. So you have 2 times the limit as n approaches infinity of 1, which is, of course, 1. So the limit from the limit comparison test is a finite positive number. It's a number, and it's positive. So we can conclude by the limit comparison test that the series for number 16 converges based on the work that we have shown. So step 3 is to state the conclusion, and I'm stating that the series that we began with for number 16 converges by limit comparison to this convergent geometric series. So we're now looking at number 18. Use the limit comparison test to determine the convergence or divergence of the series. And we have this series. And the question then becomes, what would be a good comparison test? In the previous example, we used a geometric series as our comparison series. In this example, we're going to use a p-series. And the reason for the difference is that in the previous example, our series for number 16 was, the nth term was 2 over 3 to the n minus 5. So you had 3 raised to the nth power, and in geometric series, you've got some constant raised to the nth power. So that's why we used a geometric comparison series for number 16. But for number 18, if you look at the nth term of the given series, you've got n raised to the second power. And in p series, you have n raised to the p power in the denominator. So that tells you that a p series might be a good way to go. But what p series should you choose? So you can look at the guidelines here. So you want to choose a p series so that you can disregard all but the highest powers of n in both the numerator and the denominator. So what is the highest power of n that we have in the numerator? Well, we just have a constant term, so we don't really have any powers of n there. In the denominator, we do have n squared, but then you're taking square root of n squared minus 4. So if you disregard the minus 4 for a moment, and you just look at the square root of n squared, the highest power of n in the denominator would be n to the first. And in the numerator, we have a constant term. So our comparison series will be the harmonic series whose nth term is 1 over n. And of course, the harmonic series is a p-series with p is equal to 1. So we know we have a comparison series that diverges. And the reason why we choose that to be our comparison series, once again, is because of the 2 criteria. It's easy for us to know that our comparison series diverges because it's a p-series with p is equal to 1. And you will see that when we try to take the limit from the limit comparison test, it would be something that we can do easily. Now we move on to step 2 of the process, in which we need to evaluate the limit from the limit comparison test. And you could have the nth term of the comparison series either in the numerator or the denominator, but for some problems it would be easier for you to evaluate the limit one way or the other. So sometimes you can try it one way, and if it's getting too hard for you to evaluate the limit, or you're not sure how to evaluate the limit, you can try it the other way. So if you have it set up this way, then you will have the limit as n approaches infinity, 1 over n divided by 3 over the square root of n squared minus 4. So how do you do that? You multiply by the reciprocal, and that would give us the limit as n approaches infinity of the square root of n squared minus 4 over 3n. One thing that you can do is you can factor out the constant factor of 1/3. And if you factor out the constant factor of 1/3, then that would give you the following. So to proceed from here, here's what we need to do. We recognize that n is approaching infinity, so n is positive, and for positive values of n, I may rewrite the denominator n as the square root of n squared. So if n is a positive number, the square root of n squared will be equal to n. And this is true for n greater than 0, greater than or equal to 0. And since n is going to infinity, we can do that. So now we have this. And using properties of radical expressions, I can now rewrite my nth term in this way. I have a quotient of two radical expressions with the same index, so you can write that as the square root of the quotient. So what happens now as n goes to infinity? You're going to rewrite the radicand here as n squared over n squared minus 4 over n squared. And of course, n squared over n squared is 1. And now we've gotten it to a point where we can evaluate the limit. As n goes to infinity, 4 over n squared will go to 0. So the limit that we have here would be 1/3 times. This limit would be equal to 1. As n goes to infinity, the radical expression will go to 1. So our limit is 1/3 times 1, or 1/3, which is a positive number, and therefore, by the limit comparison test, since our comparison series diverges, the series that we're working with must also diverge. And this is how we would write the conclusion in step 3. We will conclude this lesson by looking at a couple of variations of the limit comparison test. So here's the limit comparison test that we just used. And in the limit comparison test that we just used, when we take the limit of the quotient of a sub n and b sub n as n approaches infinity, and we get a positive number for the limit, then we may conclude that both series either converge or diverge, depending on the convergence or divergence of your comparison series. And again, although we did not look at the proof of the limit comparison test, I mentioned that it is in the book, and the proof of the limit comparison test relies on the direct comparison test, which we looked at yesterday, and we looked at the proof of that direct comparison test as well. So now we want to look at these two variations of the limit comparison test. So here's the first variation. If we take the limit, the same limit that we have from the limit comparison test, but we don't get a positive number for the limit, instead we get 0, can we conclude anything about the convergence or divergence of what we're considering, our series under consideration? And the other variation is if we take the same limit that we have from the limit comparison test, but we don't get a positive value for the limit, instead we get infinity, is there anything we can conclude about the convergence or divergence of the series that we're considering? So those are the two variations that we want to think about. So in the first variation, here's what we have. So suppose that we have two series. The first series whose nth term is a sub n, and the second series whose nth term is b sub n. And they're both series with positive terms. Now, if the limit of a sub n divided by n, b sub n as n goes to infinity is equal to 0, and the series whose nth term is in the denominator converges, then the series whose nth term is in the numerator must also converge. And if you wanted to think about how you would prove this variation of the limit comparison test, just like in the proof of the limit comparison test stated as theorem 9.13, you would rely on the direct comparison test. So let's consider how you would prove the first variation. This would be the logic in the proof that you would do. Okay, so we're not going to look at the details, but we'll talk about why this makes sense logically. So in the direct comparison test, we know that if you have a comparison series that converges, and then you have a series that you're thinking about, and you can show that the terms of the series under consideration is smaller than the terms of the corresponding terms of the convergent series, then because the larger series converges, the smaller series must converge by direct comparison. So using that logic, it makes sense that this should be a variation of the limit comparison test, because what does it mean for this limit, for the limit of this quotient to go to 0 as n goes to infinity? What it means is eventually, as n gets larger and larger, the terms that are in the denominator must be much larger than the terms in the numerator so that the quotient will go to 0. So what that shows is that if the series whose nth term is in the denominator converges, then the series with smaller terms whose nth term is in the numerator must also converge. And this would be relying on the direct comparison test. So you can see that the limit comparison test is justified by referring back to the direct comparison test, and I talked about why that would be the case for this variation, and you can look at the book for the proof of the limit comparison test, which also goes back to the direct comparison test for justification. So now let's look at the second variation of the limit comparison test. And in the second variation, here's what we have. We have two series with positive terms. Prove that if the limit of the quotient of the nth terms of the two series as n goes to infinity is infinity, and the series whose nth term is in the denominator diverges, then the series whose nth term is in the numerator must also diverge. Again, first of all, once again, the limit that we're considering here is the same limit from the limit comparison test, but in the theorem, you must get a positive number for the limit. What happens if you get infinity for the limit? Can you come to any conclusion? Here's what you have to consider. If the series whose nth term is in the denominator diverges, then the series whose nth term is in the numerator must also diverge. And to justify this, you would go back once again to the direct comparison test, because we know with the direct comparison test that if you have a series that is known to diverge, and the nth, and when you do a term-by-term comparison, if you have a second series whose corresponding terms are larger than the corresponding terms of the divergent series, the series with the larger terms must also diverge. And that's basically the logic that you would employ to prove this particular variation of the limit comparison test, again, once again relying on the direct comparison test. So those are two variations of the limit comparison test. Today we looked at the limit comparison test to determine whether a series converges or diverges, and at the end of our lesson we also looked at two variations of the limit comparison test.